Welcome. So you're watching a second video of me. Well, or it's your first and you didn't get the first one. In case you didn't get the first one, it's easy to find. It's the first video I ever published. Um, and the content is quite simple. It is about there is no nucleus inside an atom. And this is easily to prove. It's really easy to prove. Everybody can understand this. And therefore, I'll put a short version out here. Again, there is no classical mechanical model. And physicists tell, yeah, well, classical mechanics can't explain this, so we take on to quantum mechanics. The problem is, because the two models are interdependent, if there is no classical mechanical model, there is no quantum mechanic model. It's as simple as that. You can never, ever prove or show or even conclude that something is quantum mechanic if you do not have a classical mechanical model that you can compare against. Because the way we found quantum mechanics was we took our classical mechanical models, we made experiments, the outcome was different, and then we developed a new theory about quantum mechanics. And we could show that this is the case. So it's not about quantum mechanics not existing. No, this is not about, it is just you need a classical mechanical model that you can compare against. And you don't have this with an atom. So, this video is about what got me to the crazy idea to actually start questioning this. Because this argumentation that you just heard, I got to this after 7 years. It took me 7 years to find an argument that I could actually go out and stand against any other argument. Because if I claim something, nobody would fucking care. Nobody would care. But with real, proper argumentation, mathematical, proper argumentation, I have a chance. It's a slim chance because belief is hard to break, and physicists are highly religious. And no, not all physicists. There are a lot of good physicists out there. Let me track this back a little bit. Particle physicists. They have actually built their whole theory on a fantasy. But it was a fantasy that brought it down, and this is about I made up a model. I really say because I found finally a good argument against it, but it took me a long time. It took me almost 5 years to get an argument against it. So, and it behaves actually quite interesting, and because it sparked so many interesting ideas that are just beautiful in itself, that I want to present it here a little bit. So, let's start. You can see a blank screen, and we do, well, yeah. Geometry is the art of right conclusions on wrong figures. Well, this is an atom. We don't know what's inside. So we are going to replace the atom because we don't know what it is. We're going to replace it with a black box. Because yes, we have a beautiful symmetrical object, and we replace it with a less symmetrical object. That's what engineers do. Well, it's a black box, and so we ask, what's the input, what's the output? Okay. The input is currently not really of interest, but the output is interesting, so what's coming out of there? Okay, so we know there are electrons. That was the first one, J.J. Thomson, actually, and that's when the plum-pudding model came up. Postulated this, and actually he showed it. You can see that once you have something coming out of it, technically, it's not indivisible anymore. but human mind and stuff like this. So at the time when the Rutherford experiment was done, the atom was still atomos, which means undivisible, and that stuck for a while. Okay, so we have electrons, and then Dirac postulated his positrons, and we have actually positrons. So it's E minus, it's E plus. That's coming out. Then we have, of course, protons, and we have antiprotons. And then we have neutrons. Okay. And then we have some spectral light, kind of light. So it's visible, X-ray, gamma, light, and it's a range of range. My my imagined photon. Okay, so that's basically it. There isn't anything else. And therefore, which are the smallest? These two. I said, can I build a model only with this? Well, let's try. It's actually not too difficult. So, just like this. And so on. Well, probably not in a sphere. So there are several symmetrical ways of building this. Um, we have basically maybe some kind of a spherical, or we have the possibility of this is kind of funny because that leads to the um, symmetrical figures like tetraeder, octaeder, and so on. Um, but well, this aside, basically a bunch of, and I don't know exactly how this looks like. It is just basically alternating, but I don't know exactly how they are structured. They're somehow structured inside. And this is probably a little bit more complicated than I just did this, but you could just fill up the whole atom with this evenly spaced, and that's the model. And this actually surprisingly gives, first, it defends itself quite well. Let's ask a few questions. Is it neutral? Yes, it is. Does it explain electrons and positrons coming out? Yes, of course, they're in there. Okay, E plus, E minus. What about protons? Hmm, we know they're coming out. Well, it's actually easy. You just make the proton out of this as well. So a proton is basically a smaller atom, and it's positively charged. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Basically. And now, if you do this spherical, you can really build all these particles. So you can build the neutron, the proton, and the antiproton. Because what you do is you start with nothing, and then you build a ring. Or spherical, yeah. And you put nothing inside, so you do it something like this. So you start with basically a hole, and then you build up basically in evenly. So this is neutral, very light mass, very strong forces, kind of stable, and it has a magnetic because yeah, these particles they have magnetic poles. But there is something pure electrical charges like this one here. They are they are not stable. But as soon as I add a magnetic, I have not taken the right sum rule here into account. I don't know if the the arrow is in the right direction. Um, this is stable. It's easy. You can do this on a macroscopic scale. There are these ball magnets, and you can build stuff with it. It's stable, no problem. So that also explains stability. So stability given. What about the baryonic asymmetry? Well, yeah, problem solved. Hmm. Biggest problem of all, problem solved. There is none. Because as you can even see, positrons are antimatter, electrons are matter. There's an equal amount of them. There is none. Problem solved. So, okay. There will be a lot of stuff with this, and I will discuss all the fun stuff that this model actually gives away. But I want to start with the neutron. The neutron is one of the most interesting ones because it shows me how sloppy science actually works. So the neutron has a decay time of around 700, 900 seconds, 800 and something. It doesn't really matter. So it's in the order of minutes. And let me see if I have this here. Let me see if I have this here. Yes. So here we have it. This is the history of the neutron lifetime. Interesting. In 1950, they measured something up to yeah, almost the double of what we have today. So we have a degrees of almost 100%? No, 50%. Sorry. Oh, almost 50%. So were they stupid in 1950? Because Lord Cavendish, he measured gravity back in 200 years ago, and he was only 5% away from what we have, or less than 5% even, from what we have today. And gravity is definitely hard to measure. I think they measure it up to 4 digits behind the dot. So it's hard. And he did it with 5% accuracy. In 1950, they did it with, well, no accuracy at all. I mean, they could have thrown a dice. And then you see, and you see, this guy actually says it for fun. But doesn't that trigger immediately a really, really nagging question? Oh, yeah. And by the way, there are two ways of measuring this, and they come to different results. And nobody knows why. I I mean, this chart tells you everything. Your lifetime is dependent on your measuring method. Easy, easy peasy. Huh? This is, and then there's another question that actually, how old is the universe? According to modern, something around 14 billion years, plus minus. I don't care. So let's take a really low number, like 10 billion, and then you have a particle with a lifetime, half time, the decay time of 9 minutes. No, 15 minutes, sorry. 15 minutes, 900 seconds. And they're still around? They're still around? Are you kidding me? Uh, well, let's have a look at plutonium. Kind of interesting. So this is plutonium, and where is its decay time? Something like years, thousands of years. Why don't they tell us right away? Sweet. Okay. Find on page. Here we have. Here we are. So, 2,858 years. 2,500, 2,858 years, half time. And on planet Earth, there wasn't a single atom of plutonium until we made it. Interesting, huh? No, sorry. So this is a 260. So the 239 was the one, and it's 24,000 years. 24,000 years. And this one is the one, and this one here is the one, and there wasn't anything on Earth before we made it. And look how abundant neutrons are in the universe. So, okay, so the neutron question is kind of an interesting one. So, neutrons would make a perfect, if you build them like that, they would make a perfect dark matter because they have everything we need. They are massive and they are weakly interacting. It's a clear web. And they are neutral, but that does not mean they are not charged. And this is also something, and you could actually see this immediate because neutrons have a magnetic momentum. And where there's a magnetic momentum, there's a charge. Well, I mean, it could be still neutral, but all you have to do is look at the Maxwell equations. What there is always, it's called the electromagnetic force because one is not without the other. But somehow in the neutron, we assume it is charge free. No, it's not. It's equally charged, and it's extremely good, equally charged, and very, very, very strong neutral, but obviously not completely, because as soon as you apply a large field, it starts to decay. And so nobody knows how neutrons would actually react if they are in a field-free environment. And the space is mainly field-free. So that would explain why we have so many, because the decay time, and you can really see this. You can really see this in this chart. They had probably lower fields than we have today, and therefore the decay time goes down. So this was one of the things, and you can build this with this stupid model that I made up very, very easily. So yeah, you can explain the neutron. And then all you have to do is take one particle away. Well, let's do this. Well, actually, let's put a positive inside. And you get your proton. And let's put a negative inside. So, let's take this. So, and you remove this one, and you put this one inside, and you get your antiproton. And now the interesting thing is, if you look at the neutron, how much mass difference does a neutron have to hydrogen? Almost nothing. There's a little bit of energy, and yes, and this model actually kills the neutrino. Ah, yeah, so you can, well, I don't know the amount, the sheer amount of things that it actually explains quite naturally is staggering. So I'm not, I'm actually getting, let's do this, and white. So you have the anti-proton, and you have the proton, and of course, you can make a calculation for uranium, and then you get something like 400,000 of these small particles. But yeah, well, nobody says that nature doesn't can combine 400,000. You can also see the stability is getting, the larger this gets, because of their forces, um, the more unstable it gets. So there's a hint. And yeah, so this model gives away radioactivity. Because you know they have a moment, let's say like this. But as you know from quantum mechanics, they tend to flip. They have a certain probability they are going to flip. So if they are going to flip, and the magnetic field is the source of stability, not the electric field. The electric field, we know, is not completely stable. There are some certain configurations that are stable, but in most cases, this is shown to be electric only is not stable. But with magnetic field, it is stable. But if you now start doing something like uh, flipping one, you get basically a disorder, and that will give cracks. There will be happening a lot of stuff, and some particles might get kicked out because of the strong forces and the light masses. Um, yeah, so you have a good, really good start up for radioactivity. And this is what what particle physics is probably like. You can bind radioactivity directly to quantum mechanics. Radioactivity. Okay, you don't need the neutrino. Kill the neutrino. Well, I made this a little bit too early because I should show you how. What is a neutrino? A particle. No, it's not a particle. The neutrino is a postulated particle. It comes actually from, I think, barium beta decay or something like this. So what they did is they measured the energy, and after they measured everything, some energy was missing. And they did not have an explanation. And so Wolfgang Pauli, he proposed, well, it might be a particle who carries away this. With this model, you do not need this. You do not need any neutrino particle. Because let's say I have a somehow structured, I don't know how it's structured, but somehow structured, and you can imagine with positive and negative particles, they must be alternating. So now you take one away. It's a beta decay, so we take one away. Let's do this. Okay, what happens to the rest of the particles? Well, they rearrange. They rearrange. And this rearrangement, what does it mean for the average distance between two particles? Well, it's also quite simple. You have basically the same volume, and you have one particle less, and that means the average distance between, oh, sorry, between these two particles is increasing. But these are attracting forces. What happens if you increase the distance between attracting forces? You increase the potential energy in the system. And therefore, there goes your energy. You see, for fantasy model, not bad, huh? Not bad at all. Okay, let's make a little bit room here. It's kind of fun. So I want you to have fun with this because none of this is actually real how it is. I'll show you later on the counter argument. But let me address the elephant in the room. Shouldn't this go up in a big flash? And the surprising answer is no. Um, the reason why this is not true is a different one. So, what about there's a simple experiment. Well, actually, so it's been measured, and it's you take two of these particles. Let's take. Well, let's make a new. So you take one particle here, and you take one particle here. So the likelihood they have exactly the same speed towards each other is extremely. So they have something like this. But they are light, they are attracting each other. So what are they going to do? They are going to spiral in each other. I think something like this. Okay. And then once they here in the center, then we see these two gamma rays and the particles are gone. And the energy of the gamma rays is exactly the energy of the electron. Problem solved. So, but actually what happens here? We don't know. And of course, now I had a fantasy model, so I had to ask the question, why isn't it going up in a flash? And that led me to something really, really interesting. Because if you draw a timeline, let's draw a diagram. Well, uh, yeah, I know there's a function. I can make it something like this. I haven't activated this. It's a really bad axis. This is a little bit better. So we take the time here, and then you have, which is, let's say, here, and then you have the time where they meet. And that's the time when you see our gamma rays. What happens in this period of time? This is a curved motion. A curved motion is an accelerated motion. And what do charged particles do if they are on an accelerated motion? Yes, they emit something that is called, and from my accent, I can perfectly pronounce this, Bremsstrahlung, which translates basically to deceleration radiation. So whenever, because the particle is basically losing energy, but this is never observed. Somehow the particles decide, hey, it will be in a short term, I'll be meeting my mate, and then we will anyway radiate. So we don't need to radiate. This is completely missing. Okay, this cannot be. Electrons are no humans. Electrons don't think. Electrons behave according to the laws of physics. And therefore, the missing Bremsstrahlung and the gamma ray that we see must be the same. There's no way around it. And it's actually, well, you could say, well, this is frequency independent and broad, but you see, if this is a very light particle, the forces are extremely strong, so the acceleration is extremely strong, and therefore the whole radiation, the energy loss, exceeds the loss of energy, exceeds the whole energy that's in the system. And that's why we see a quantum radiation. Because You cannot just grab energy out of thin air. Bremsstrahlung is taking up all the energy, including the mass. That's the simple explanation. But that means if they are in a field where they actually cannot accelerate, so inside an atom where they are in a grid, they can perfectly live together. That was the explanation. If this is true, if you find some counter arguments, well, okay, be my guest. There are comments down below. But this observation that there never, never, ever has been observed any kind of Bremsstrahlung, well, it should be addressed. And you could say, well, actually, I asked this on Stack Overflow once, and someone told me, well, behind on the background of the strong gamma ray, it would be hard to see. Well, no, actually not, because we have no problem measuring here. Well, this did not happen, and it's not there. So you cannot say, hey, I can't measure here because something really, really big is happening here. Oh, you can measure that, and it's not there. So this must be your Bremsstrahlung. That's the only explanation. This is basically like Sherlock Holmes. If anything impossible has been excluded, then what's left must be the truth. May it be unexpected as it is. So this was stability. This is actually going into stability. No, no flash. Okay. So what else? Oh yeah, it's that one actually it really blew me off. Let's have a look on the surface. So on the surface, obviously we have something like hydrogen, which is a little must be oh yeah, as I said, this answers so many interesting questions. That means that the neutron and hydrogen must be roughly in the same scale. So the hydrogen is probably a little bit larger than the neutron, but not by 3 orders of magnitude. Maybe 10, maybe 20%. So it's slightly, so this is, and then there is a new basically shell opened for hydrogen. But so this is an, and then we have, yeah, so we basically do the proton and then we add another electron. Yeah, here, which gives us hydrogen. While if, so the difference is you have a positive core and then you build your thing to a neutron and then you add one electron to make it, sorry, you build everything to a proton and then you have an electron and that gives you your hydrogen. And while the neutron, you start with nothing and then you have equal amount of charges. And for some reason, obviously the neutron is very is a little bit, maybe it's a little bit more tighter, but maybe it is 10-20% in size difference. And yeah, we don't have any experiments for this. We will have we will ask the question for helium as well. That comes next. So what did I forget? Yeah, so what really blew me off was I found a publication, something in 2003, of someone who could map the 2n square electron configuration through the Thomson distribution. So the Thomson distribution gives you the natural to n square configuration. And we all know we're calculating the shells like this. And if you go for the Thomson distribution, so how would this behave on the surface? Like a Thomson distribution. Even if it's positive and negative, that would still not matter. They would still try to distribute evenly as possible on the surface, and then you have these weird behaviors like if you get 8 on them, if you get 8 on the surface, you can also fit 9, 10, 11, and 12. And then extra number 13. There have been mathematical publications about this. This is actually also a question. The Thomson distribution is also a question in nature when you have seeds on the surface of a plant and all these kind of things. Uh, but getting something like this out of a model that I invented, I just made it up. Okay, it's natural. You take the but then you try to follow what it where it leads to, and you get all these interesting fits, and then you get a lot of interesting questions. As I said, helium. According to the modern theory, helium is an alpha particle with 2 electrons. Helium is quite difficult to make. I think the US is still leading in helium production, but helium is really, really difficult to make, and it's quite expensive. On the other hand, alpha particles, there is an abundance on Earth. There are so many alpha radiators out there. Also, electrons are actually really easy to make. So why don't you just take an alpha radiator and you just couple it with a stream of electrons, and they would naturally form helium, which is the most stable atom on Earth. It doesn't happen. It does not happen. I mean, you have this theoretically cheap method, and it doesn't work. Why doesn't it work? Yeah, because very likely helium is not an alpha particle with. And if you take the proper, it's also the alpha particle explanation is really strange because the explanation is it's 2 protons and 2 neutrons, right? Have you ever tried to get the symmetry into them? Any kind of symmetry, like well, you could put four particles. You could do a tetrahedron. Tetrahedron could be, but that's not symmetrical. You can put 2 next to each other and the other 2 on the opposite side, or well, there will always be there could be there would also there would be a disk. There wouldn't be. You cannot make this symmetrical as a sphere. And yet, has any asymmetry ever been discovered on alpha particles? By the way, actually, alpha particles is one of the things that actually will bring down my model, because the alpha particle is a super mystery. This is an extreme mystery. You will see. But so yeah, you can explain this one. You have a Thomson distribution. Distribution. Um, yeah. So what else do we have? Mm, Well, I think this is mainly. Oh yeah, of course. Um, the radical. A radical is a chemically really interesting element. It's an atom. It is neutral, and yet is highly aggressive. Well, this one here. So this is P plus. This is E minus. E minus. Let's take it white. Who cares? That is hydrogen. And you can already see this is not fully symmetrical. So it is a sphere, but it must have some kind of, so it looks a little bit more like a water drop, and it is very clear that this one, also neutral, is extremely aggressive. And once you put a second one, that eases out the situation a lot. So H2 will be a lot more stable according to the theory. Simple. Water. I actually thought, but it's, as I said, this is my fun project for if I'm bored or at the bus station and do not have internet or whatever. Um, I'll do this. So it's just fun. But if you if you look, that model actually gives you a good explanation why we have a water angle. Because if you take something like this and then you put an hydrogen and oxygen in between and then another one, yes, this will not be stable. This cannot be a straight line. So it will flip to one side. And I thought maybe because of the forces, there is a chance that we could calculate that angle. But it's not that easy as it sounds because it is a question of how how much surface do we have. So the oxygen would come from here. And how large this surface area here is highly influencing this, and this is way beyond my Gedanken experiments. But if someone actually wants to calculate this and actually try to get the water angle, and then not only water angle, and there is fluorine, hydrogen, and with sulfur, I think there are a bunch of these three atom molecules that form these kind of angles. And yeah, that would be interesting because I think it is probably something in this direction, but I get something really, really basic wrong. So let me just, why is helium such a mystery? Well, helium is not a mystery, but why is the alpha particle such a mystery? According to this, everything is fine except alpha particles are actually quite stable. So how is it possible that a small particle has always a 2 plus? I mean, this is not just 2 plus. The electromagnetic force is extremely strong. It's extremely strong. And therefore, putting two charged particles in there, yeah, in the end, I'm going to end with a strong force again, which is stupid. I really don't like this. There must be some other explanation. It's also well telling that it is only with 2 plus. You never see this with 3 plus. Mm, uh, maybe maybe the alpha particle, which is basically 4 times the mass of a proton, plus I think plus 2 electrons. Maybe this is an exceptionally stable configuration that can withstand the forces, but nevertheless, somehow that does not make really sense. It's just the weirdest particle of all. A single proton, yeah, you can explain this quite easy, especially as proton and electron form a neutron together. That theory actually just, and the extra energy, as I said, goes into the the different configuration. So the rearrangement of the charges actually changes the average distance, and that's where the energy goes. So, but for the alpha particle, and also alpha particle plus 2 electrons does not give you helium. Otherwise, it would be super cheap to create helium. Because, as I said, there is so much natural radioactivity on Earth. Electrons are easy to produce. You just take a stream of them and a stream of electrons, and in the end, you should get helium, which is not happening. So, yeah, this is the biggest mystery of all. And then there is, of course, the actual elephant in the room, not the flash. You take a simple battery. Let's take a simple battery. And you take a light bulb. Okay. And then you take a wire and another wire. Oh, well, and let's the switch. And then you close the switch. What is going to happen? Well, you see a lot of these. You never see these. They are not there. There are sometimes circumstances under which these particles are emitted from atoms, but not with a simple electrical circuit. This model has zero explanation for this. Zero. If you put an electrical field in form of a current onto this, electrons should go in the one and positrons in the other direction, and it's not happening. There are only electrons. And therefore, this model is wrong. This is as simple as that. But the amount of shear, as I said, you can even explain dark matter by building the neutron like this. You can so this is also really interesting because of this no Bremsstrahlung. You get a completely new idea about the Big Bang. The Big Bang is usually in the beginning there was light and light formed matter. No, this one tells us, uh-uh. This one tells us in the beginning there was matter. And the universe is not getting darker, the universe is getting brighter. Because matter is slowly eating up itself. There is 50% of matter, there's 50% of antimatter, and once they have the possibility to emit these strong Bremsstrahlung, they will convert matter into light. So there is a constant stream of matter getting turned into light, and that light is then radiating out. And so the universe is slowly losing its gravity. That's why we see this, possibly this expanding. So you see, wrong, or might be wrong completely, might be, but at least what I said, the beauty of the ideas is just amazing. And this model actually gives a lot more, like, oh yeah, you have a really, really good explanation for is it called? Is sub-zero currents. So, so beyond a certain temperature, currents start to flow without any resistance. This model is just perfect because you have all these, because you have a lot of small vibrations here. But once it's cold enough, these vibrations stop. If the vibrations stop, a lot of the electric field is stopping. The magnetic field is stopping. If there's no magnetic field, so supraconductivity. So supraconductivity has an easy explanation in this. Yeah, no movement, no magnetic fields, only the static ones. But the static one doesn't have that big of an influence. I mean, it's quantum, and then it's complicated stuff. And this is actually not physics, what I'm doing here. This is not. The fact that there is no nucleus inside an atom, that is true physics. That is absolutely bulletproof. I wonder if anyone would. I mean, so the problem, you see, I got it out. Nobody actually dared to argue against it. Nobody dared it. There was no no one who really, really dared to argue against it, because you cannot. The argumentation is really, really bulletproof. But this one is, well, I made it up. But the general ideas and the questions that have been asked about it, they are, I think, in general, kind of interesting. This turning around, like, might the universe eat up its matter, like the sun does with certain. This this model also explains very well the particle zoo, because you can build basically any particle with any mass and it will not be stable. So there seem to be some kind of stable configurations on certain sizes, and everything below is possible for a short time and then decays again. And that explains why we have so many particles. There's another interesting one that that is actually held, which actually also blew my mind. Well, because everything is this kind of yeah, it's my baby, I like it, and I'm biased, and all the kind of stuff. But there is another interesting experiment besides the Rutherford experiment, and that is you shoot electrons. And then you get this interesting curve of, you get three different reflection curves. reflection, deflection, but it's three different. The explanation was, well, it's the quarks. My explanation is, no, it's just three different charging zones. Because this one, what will it create? There will be a zone that will be mainly negative. Oops. So it will be, let's start with positive. So it will be mainly positive. Then there's another zone that will be mainly negative. And then there's a third zone where we have this in between, where we have basically neutral behavior. Could this give such a curve? Yeah, of course. Because, yeah, they would probably um, insert themselves. This, by the way, is also extremely misleading. I mean, um, they are probably less dense than the asteroid belt. It was already very clear, already at the time of Thomson, that the atomic mass and the volume gives extremely low density. So this is an extremely misleading image or picture. There's huge space between them. And now, if you take this and you take this and you shoot them against each other, they will very likely never hit each other. They will just go through each other, which explains why you can actually shoot things through atoms. Okay, you can ask the question of, wouldn't this actually make any problems with stability? Possibly, possibly not, we don't know. But there's another thing. But why do we have reflection? Because one thing I criticize a lot was the Rutherford experiment, but one thing is undoubtedly there is reflection. So there are two possibilities for reflection. First of all, it's not alpha particles. Something else is coming back. We don't know because we are only measuring ionization. So do we know it's alpha particles? No. Let's assume it is alpha particles. Well, normally they would just go through. Rarely, one particle would hit. But now think about it. It's basically, if you look at them, it's basically some kind of a grid. Some kind of a grid hitting another grid. Possibly rotated, but even if rotated, if one hits, because they're all even spaced, others hit too. So suddenly, if they match, everybody hits. If they're rotated, a portion of them hits. And this is also what we see. We see very rarely a complete reflection, which means in this case the angle is mainly identical. So this one would be actually on top of the white, so the red one would be on top of the white one. But if we see a partial, so this might be rotated. And then only every fifth or every tenth or every 20th would hit, which would then lead to some different behavior. So it's not out of the question that might actually, there might be something. But the main reason the Rutherford experiment is not valid anymore is we have no indication that what is coming back is actually alpha particles. Second, we are not looking for any kind of fission. So you should actually start doing spectroscopy while you're shooting the alpha particles, because alpha particles have the tendency to cause radioactivity. Yeah, so um, so we don't know. Let's say these reflections are actually part of a fission of gold atoms, would we realize this? That the gold is slightly less now? A few atoms are missing. I think it's one every minute. I mean, this is nothing. 1 mole uh, of gold is 10 to the power of 23. Who would care? Nobody would actually realize if you take away a few gold atoms. So, no, there's a lot of things that is not valid with this anymore. And what you should do is your detectors should actually be behind an electric field or a magnetic field to see how they are deflected, so you can actually look for the mass. You can filter by the energy that they have and all the kind of things you have to do. The experiment was a good idea in 1911, but nowadays just blindly repeating it is we have more knowledge about it, and therefore we should take this knowledge into account. So the Rutherford experiment is not valid nowadays, not in its current form. You can improve it. If you're a young student, these experiments are actually not too difficult to make. You can buy the Rutherford experiment off the shelf. Now you say, hey, why don't I do this? Well, actually, we live in interesting times, and what do you think if I start ordering radioactive materials at home? Do you think I get radioactive materials delivered at home, or I get a SWAT team in front of my door? Well, yeah. So let's keep this in universities. They have the right to do this. They should do it. They should start modifying this experiment to exclude possible variations that might be possible. It still might be really coming back. But actually, Rutherford already foreshadowed it. He said, it's like you shoot a 15-inch shell against a tissue, and it's coming back. And common sense tells us 15-inch, actually, this was the guns of Hood, HMS Hood. She had 15-inch. Rodney. So these big British battleships. If they shoot something, their shell is not coming back. No way, no branch molecule movement, no any theoretical physics will make this shell come back. And that should actually make us think. What's happening here? So yeah. Okay. So this is what got me the, as I said, the lack of asymmetry, which is the only thing the original atom model really shines. Because with the protons and electrons, the question is clear. Yeah, only electrons, because the proton is 3 orders of magnitude heavier. That's clear. But my stupid model does not have this. And therefore, I need a proper explanation for why I don't see positrons all the time. So basically, the question for the baryonic asymmetry is only, well, it's basically I kicked the can further down the road. It's not an answer. But it was fun. It was super fun. And I hope you had fun. And I hope you get inspired by start asking questions. Think for yourself. Because physics obviously showed you what a perfect brainwashing machine it is. Because a lot of this stuff is very, very obvious. And if you are dealing with this every day, you should have found it. This is not me. I started this 7 years ago because I had insomnia and I did And I was actually intrigued by the question about dark matter, and the question, why don't they actually look for gravity? Well, yes, gravity is a little bit difficult, but it's your best chance because that's what we have. And then I actually asked the question, why it's not neutrons? And yes, of course, I mean, I got this. Well, you have this little decay time, but I said, aren't there any experiments? Maybe cold neutron. You could actually shoot neutrons from one satellite to another. You can use these slow neutrons and then check if the decay time is the same because you can space them apart a couple of 100 kilometers. So experiments like this could be done in free space. Are neutrons really decaying in free space? And get what my wild guess is no, they won't. It's your field that makes them decay. Otherwise, they are really stable because otherwise you wouldn't have so many around after billions of years. So natural. Yeah, so um, this is basically the documentation about 7 years of having fun and starting interesting questions. I don't think I will um, continue on this too long because yeah, I've said everything. I maybe I forgot a few interesting traits, but if this is actually the start for you as a young physicist and actually starting questions, starting making calculations, starting to make new experiments, you have now a rough idea what might be actually promising. You have to find, of course, an answer for this missing symmetry. That is really an interesting question. Um, there, there is one more I will do on the particle wave duality, which is also one of the things that I stumbled upon because of this, but that's another video. So I thank you very much for your attention and hope you had a lot of fun with this one. Thank you. Bye bye.